Again, how do we pay for development? I think that's a subject that the industry ought to put on more of their state-level conferences, invite specifiers and contractors to get together and seek better ways of being able to handle that. Okay, now we'll take a look at 4 case studies that take into consideration some of these techniques that I mentioned earlier in the talk. First is an older study, but to me it's a very time-proven study that has to do with matching the development technique with the screen device. In the 1980s, the Division of Energy Conservation, part of the Department of Energy, undertook a $1.5 million study that was centered on improving efficiency in irrigation. Part of this study was a well efficiency project that was done near Staples, Minnesota, in conjunction with the Agriculture Engineering Department at the University of Minnesota. And it involved 6 wells that were drilled, different methods, and completed with different devices. What this slide illustrates here is these were all drilled in the certainly the same geological location. You drilled a total of 6 wells. You drilled 3 wells with bentonite, and you drilled three wells using revert, which was a polymer drilling fluid. 2 of the wells were completed with low open area mill slot, 2 with bridge slot, and 2 with wire wrap screen. And what they did was each well was then developed first by overpumping, then by surging, then by jetting with airlift assist, and after each phase of development they test pumped to measure the results. Here's what the findings were of this study. First, the upper left-hand graph, taking a look at how the wells responded to a more aggressive technique. In other words, first we overpumped, then we surged, then we jetted. What happened there was they saw improvement every time a different technique was applied. Aggressive mechanical agitation resulted in overall average specific capacity increase of 23%. So that suggests certainly that getting more aggressive with the development technique, again, like I said, adding all these techniques, they're more costly, that's money, that might be a contractual issue. This slide here represents looking at the impact of the type of drilling fluid. What they saw was the wells that were drilled with the synthetic polymer responded right away much quicker than the other wells, even though in other words, they developed up quicker, even though there was a slight improvement after you added more agitation. So what the net conclusion of that was that wells drilled with polymer drilling fluid yielded a 24% higher specific capacity on average when you looked at all of them. So again, implies if you use a proper drilling fluid, that's going to come into play. And the open area, how did the open area of the device stack up? The bottom line was when you had more than 15% open area with your screen device, you had on average a 52% higher specific capacity than when you had wells with below 15% open area. So looking at the net effect of jetting and overpumping, the different types of screen, the higher the open area, the better the result. And what that basically really added up to was getting to the jetting techniques. That's going to really pay off only when you've got a screen device. To meet the city of San Antonio, here's another case where this involves a pre-pack screen. We talked about pre-packs earlier. To meet the minimum well efficiency, construction records for 3 conventional gravel pack wells completed in one of their well fields indicated average development time was approximately 1 hour per foot of screen. So they were interested in looking at MuniPack and whether or not it would work in their well field and afford them as good a production and maybe some advantages. So conventional well was represented here on the right. Their conventional wells were 16-inch screen and a 24-inch borehole, and the MuniPack construction was a 16 by 18-inch pre-pack inside a 20-inch borehole. Both the wells pumping at 1,400 gallons a minute. The conventional well produced with a little over 30 feet of drawdown, so a specific capacity of about 46 gallons per minute. The MuniPack well had 24 feet of drawdown and a 58% specific capacity. So the summary of the results that they saw was they were able to reduce the borehole diameter by 16%. Development time fell 37%. The drawdown decreased a little over 20%. And so we got an increase in specific capacity a little over 25%. So the city was well pleased with the results, the way those turned out. Here's a small well. I brought this one in the picture because a lot of small wells drilled, a lot of people use bentonite, a lot of people have problems with them. This was to be a monitor supply well in Shagaluk, Alaska. I put the map in here because I had no idea where this was when the guy called me. This was last summer, July of '09. Again, it's a very shallow well, total depth of 110 feet. It's had a pitless adapter to a depth of 10 feet. From there, it was a 6-inch construction, a hybrid well, PVC pipe down to 93, and then a K-packer into the pitless. And on the very bottom, you had 10 feet of 20-slot stainless steel screen. It was drilled in coarse sand and gravel with clay, and the driller noted that he lost circulation during the drilling process. His comments were he had to stop frequently because they were monitoring some conditions. He had to stop frequently to test, and again, losing circulation. So in talking with him, I was pretty convinced that he just had mudded up the formation and had it plugged up. Initially what he had done was he'd used his baler and he'd used AquaClear, which was a chemical compound that's a surfactant basically meant to break down bentonites. And then they'd put a submersible in and pumped it, and we're getting less than 1 gallon per minute flow. To me, where this got particularly interesting, and the little story I tell people here, is that I had several ideas. I asked the gentleman after I'd talked to him for a while, said, okay, what's your email address? I'll send you some thoughts and ideas and some information. Well, he didn't have one where he was. I said, well, have you got a fax machine? Well, yeah, there's a fax machine at the post office, or not the post office, it was at the general store, but it wasn't working. So we arranged every day at a specific time that we would have a phone conversation, because the drill site was approximately a 2-hour drive from this little town. So he was out in the middle of the boondocks. But what we did was I had him get a hold of some chlorine solution, went in and introduced chlorine basically to break down the polyacrylamides, and go in and surge that with his baler on a daily basis. This went on and off for a total of 10 days. Again, like I said, we were talking every other day, and he was getting excited because they were seeing debris come out of the well. So bottom line was he got a 6-fold increase in the well, and he was able to overcome the fact that he had severely plugged it off with mud and stuck with it. Again, here the unfortunate thing was he couldn't move over and just re-drill this well right first. That was my initial recommendation, but they had to have the well right where it was. But I think that's a good example of the use of chemicals and balers to overcome a difficult situation. Here was a well drilled in southern Colorado. It was for a fish hatchery. And in this case, you had no drilling fluid damage because they drilled it with a casing advance system. So in this case, it was to be a 12-inch completion. They first advanced 18-inch casing down to total depth and installed 12-inch screen and casing. This was in a alluvial riverbed with approximately 40 foot of production zone, and they were looking for 380 to roughly around 400 gallons a minute yield. Initially, they had a development program. They airlifted the well for 4 hours until the discharge was free, and installed a test pump, surged again with a test pump. So here we're using multiple development techniques, but at the end of that, they were only seeing about half the production that they thought they should be getting. So what they concluded was, even though there was no drilling mud used, they were getting liquefaction of the formation during the drilling process because of the vibration. The bottom hole airlifted cuttings caused depressurization at the bottom of the borehole, and this liquefied fine-grained sediment moved toward the outer casing by moving from areas of high pressure to low pressure, so this damaged the formation further. And now they decided they needed further development. So they came in this case, they used a clay dispersant, so again introducing some chemistry, and they swabbed this into the formation, so brought in another development technique, surged it again for 6 hours, an airlift pump for 2 hours, and they noticed they were getting clays and silts out of there that they never saw in the initial development. So again, the addition of chemistry aided the whole process. Did bring the well back to the anticipated yield. So in this case, you had a drilling method that excluded drilling fluids, but you still needed to add the chemistry in order to overcome drilling through the silts and clays in the geology. So why is development important? To me, I think we've pointed out that development process determines the successful or unsuccessful completion. It can impact the quality of the water being produced. I point out here that the state of Michigan concluded that wells properly developed had fewer problems with positive coliform tests. So development can not only impact the production, but also the quality. It has, I think we've pointed out, it can have a major impact on yield and specific capacity and therefore efficiency, which can have a financial impact on and operational cost of the well to the owner, and it can also affect the useful life. So that's where I'll wrap up. To me, development it's definitely an investment in efficiency. We shouldn't take shortcuts, and that's what makes a hole a well. So thank you for your time.